Okay, hello. We're now live.
Hello.
Hey everybody.
Hey guys.
So welcome to the weekly stream. This week we're going to be writing an event dispatcher. We have with us in the chat we have Thibaut, we have Samuel, we have me, Joshua, and we have Alex.
Hey guys.
Hello, hello.
So in B we have a requirement to send various events around about things that are happening. So things like transactions that are being received, or changes to the state of the ledger and stuff like that. And so we need a way to be able to send events around the internals of B. And the typical way to do that in Rust is to use a thing called an enum. So an enum, or a sum type if you're from the Haskell world, is a type that has multiple inhabitants. So you can see that this event type here has two inhabitants, foo and bar. So that means that if you have an instance of that event, it can be either of these two options. Now this ends up being quite useful because it means you can represent one of multiple options. C has enums as well, but they're strictly less powerful than Rust because Rust can do things like adding fields to each of the items, the variants they're called. So we're going to explain the sort of the naive method of implementing an event system first, and then we're going to do it a bit better. So the naive way is to just have a single event type and to have all of the variants that represents all of the possible events that could occur. Now we've got this type called bus, which is the central event bus. So it's basically being used as a dispatcher for all of the events. So it gets past events and then it throws them out to everything that needs to listen to them. So we have these two methods. The first is dispatch, and the second is add listener. And add listener will take an event type and a function, and it will call that function whenever an event is dispatched that's of that type. So this seems to work great. So if we're inside another B crate, we'd import the event type and the bus, and we dispatch event, and we can listen on events, and this is great. But the problem comes if we want to have other kinds of events. So for example, we might want a third-party crate, a plugin, to dispatch events into our event bus. And now we have a problem. Because event is defined up here, inside our event crate, we can't add new variants to it because the API of the event crate is set in stone. So this becomes a bit of a problem because it means that we don't have a very extensible system. So we're going to try to resolve this, and we're going to resolve this by allowing each event to become its own distinct type. So I'm going to switch to a new file now where we're going to start implementing this stuff. So we're going to start off with our types as previously. We're going to have our bus type, and we'll find out what to place inside there in a minute. Should be a struct. But this time, rather than an event type, we're going to have an event trait. And this trait is going to be implemented by anything that is an event. So if you're used to object-oriented programming, it's kind of similar to an abstract class, except except it's a bit more powerful as we'll soon see. So we're going to create this event trait, and what we're going to do is we're going to require the implementers to define a constant that is the name of the event. So the name of the event is going to be a string because it needs to be nice and easy to read, so that if you're trying to debug things and you want to output the name of the event, it's quite easy to know what it is. So we're going to require that it declares a constant. So this is going to be a static string, which means basically just a string literal like that. So next thing to do, we've got our event type. Now we're going to add some methods to this event struct, to this bus struct. And the first one we're going to want is a way to create it. So an easy way to do that is to derive the default trait on it, which will give us a default way of creating it. So we can go like this: bus default to create a bus. Fairly simple. Okay. So now the next thing we want to do is we want to be able to dispatch an event. So we're going to create a dispatch function. It's going to take self. It's not going to take self-mut because we want this bus type to be used from multiple threads and multiple tasks within B. So it needs to be immutable, and everything inside needs to have internal mutability, which means it's able to function even if it's being accessed by lots of independent threads at once. So it's going to take our event that we want to dispatch, but this time, because event isn't a concrete type, we're going to make it generic over all types that are an event. Okay, so we don't know what this contains yet. And we're going to want another method, which is the add listener. So there's an interesting thing we can do here. Previously, we had to specify the event type that we wanted to listen to by giving an example of it, and that's okay, it works fine. But the problem here is when we start to want to add fields like that, for example, if we want to listen in on a foo, we've got to then provide an example of foo, right? Which is a bit strange because that's not what we want to do. We don't want to create an example of foo. We just want to say we want to listen in to all foos. So instead, we're going to make this method generic over an event like so. And now it already knows what kind of event type we're trying to listen into. So then we want to allow it to accept a listener function. So fnmut just means it's a function that can mutate things in Rust. We're also going to want to make this send plus sync. In fact, do we want to? Yeah, I think send plus sync, which will mean that it could be sent across threads, basically. And it's going to take our event type E, or an instance of it, and it's going to do something with it. So this is our handler function. So the signature is getting a bit long, so I'm going to put it onto 2 lines, or more than 1 line anyway. So we don't know what goes in here yet. So first of all, we're going to write some tests, because it's always nice to have some tests to sort of get to grips with how your code works and make sure that it's doing the thing you think it's doing. So the first one is just going to be a basic test, which we're going to develop as we go, and then we'll branch it out into more tests later. So the first one is going to be to create a new bus that we're going to put an event type up here. We're just going to, no, I'm doing the old kind of event. So we have this event called event A. In fact, let's call it event foo. It's a bit more easy to understand and think about. And it's going to have a name, of course, that is going to be used by the dispatcher, and that name is just going to be foo. Whoops, I've named things wrong. We're also going to create another event. It's going to be called bar. So the reason for this is just that having more than one event allows us to interleave things and check that it's properly dispatching it in the right order and stuff like that. So, there we go. There are two events. So first of all, we're going to add a listener for one event. So we're going to do bus.addListener, and when it receives an event, it's going to give us, it's going to say received a foo, and we're going to make it listen in on event foo. I'm actually renaming these because these are a bit annoying. I'm just going to call them foo and bar directly. And then we're going to do bus.dispatch, and then we're going to give it a foo. So in this case, what we expect to see is it's going to go through here, it's going to add the listener, it's going to try to dispatch a foo event, and then it should print this in theory. So now our task is to implement this bus. So the first thing we want to do is, we don't really want to be looking up the string name of the event, because strings are quite complicated to look up. You need to check all of the characters to make sure they're the same and so on. You've got to go through long lists in order to check the names are the same, or you can hash them, of course, but hashing a string is still quite a long process, and we don't want to do that. So what we're going to do is we're going to intern the strings. So interning is a technique where you take a more complex data structure and you squash it down, a bit like a hash. You squash it down into this value that's really easy to work with and compare, that's completely unique to that instance of the original data structure. So in this case, what we're going to do is we're going to turn our event name into an interned value, and in practical terms, an interned value is basically equivalent to just a pointer, and you can check it for equality, and it will tell you whether they're equal, of course. So the way we're going to do this is that we're going to make it automatically intern this name. So we're going to create a method that has a default implementation for event, and that is I'm probably going to be renaming this later, but this will do for now. And this is going to give us an interned string, which corresponds to this string up here. So the interned name of the event. So we're going to do this using a thread local And a thread local is a value that is local to a given thread, and it means that if we're using the event multiple times, or rather if we're calling this multiple times, we have an independent one for each of them. I'm not sure that made much sense, but you'll see what I mean. So, make the text a bit smaller. I assume it's still visible. Is this still visible? Hopefully. So now we've got this interned thread local, but it doesn't actually intern the name yet. So we need to do that. So intern name with and what we're going to do now is we're going to check. So this interned name can either be a none or a sum, because a none or a sum because it's an option, and that means that you can either have an interned string here, or you can have nothing. So there might be cases where we've not interned the string yet, and we want to do it the first time we want to intern it. So what we're going to do is we're going to pattern match on this. We're going to see whether it's a none. If it's a none, then we want to actually perform the interning, which means you basically insert the string into a global hash map, and then you get back a pointer to it. So the idea is that this path is only going to be taken once at the very first time that this function is used on this thread. So this is quite a useful thing, because it means we're doing the minimal work. So we're not even allocating a string most of the time. So now we have ourselves an interned string. So that's great. That gives us what we want. It's really, really cheap to call this. In most cases, it's basically just fetching a single integer, and we're going to use this in our dispatcher. This is nice as well because it preserves the ability for events to have names, which is really quite useful when debugging, and it's useful for third-party crate users and so on. So next we're going to implement the bus. So I'm going to cheat a bit here and refer back to a prototype I wrote earlier. That implements the bus using a hash map, except in this case we want it to be concurrent because we only have an immutable reference, so we're going to use something called a dash map, which is a data structure that's it's basically like a concurrent hash map. So and then we're going to have a list, or we're going to have a mapping between, let me just check, is it with a capital? Yes, it is with a capital. I've done that right up there. Good, I have. Right, so it's going to be a mapping between an intern string. Remember, this is effectively an integer. In terms of hashing it, in terms of looking it up, in terms of moving it around in memory, it's just an integer and it'll fit inside a single register. So it's really damn quick, basically. So this is going to be mapped against, and now I'm going to cheat a little bit, and I'm going to use a mutex here. Later on, I'm not going to be using a mutex, and I'll swap this out at a later date with something that's a little more performant in most cases. But this will do for the live stream. And the mutex is going to contain a vector of event handlers. So what we want is this signature here of a function that takes an event, but we can't have this event here, because the bus has no type parameter, only this method does. So what we're going to do is we're going to wrap the event in something called an inner event, which is a type that I'm going to write now. One moment, I'm just going to right, there we go. So that's a function that takes an inner event. So an inner event is going to be a thin wrapper around a boxed event. So in this case, event is a trait object, which means it's doing dynamic dispatch to an implementer of this trait. So it's going to take an inner event, then it's going to do something with it. So in this case, we've got to create one of these listener entries that corresponds to this handler. So first of all, we're going to do listener dot one moment. Right. Actually, what I'm going to do here is I'm going to remove the mutex just because I don't think it's needed in this case, actually. But I might change that later. Right. So we're going to search using this key. The key here is the intern string. So we're going to do E, because this is our event, E get interned. We're going to take a reference to it because this method takes a reference. And now, oh, actually I could use this. That's a good point, actually. I might use a special API that DashMap has called the entry API. An entry is like fetching entity. It's like fetching an entry from the hash map, but it allows us to do a little bit more with it. So I'm going to do .or default. So if there's no entry for this particular event type, we're going to insert the default, which is just an empty vector as shown here. And then we're going to push our event handler. So box new. So we want to push our handler. However, we're going to get an error because this handler does not have the same signature as this. So what I'm going to do is I'm just going to keep this here for now, and I'm going to compile it. And then in this method, I'm just going to add a to-do so it actually compiles. So can I go to the terminal? And I've hidden it behind something else. We go, right. Right, we're probably going to get quite a few errors here. There we go, yeah. Okay. The first one is a syntax error because I've done something silly. Yeah. Okay. I've also done something silly here. I've added a colon when I shouldn't have. Right, okay. And yes, it's absolutely correct. I should have done self.listener. Okay. Right, what I probably should have done is I might move this constant into a method actually. This will mean that I don't, or rather at the moment the constant is preventing us turning it into a trait object to allow us to do dynamic dispatch down here. And so we want to not have it block that. So what we're going to do is we're just going to define a method that does basically the same thing, but this method is only going to be enabled when we're not doing dynamic dispatch. So we're just going to change this. Okay, let's see whether it likes us now. Okay, yeah, I should have done exactly the same on here as well. Okay, and now of course because I've gotten rid of the constant, I've got to change it to the method version. Okay, right, so now we have the error that I was explaining before. Okay, we've got a mismatch between the type of the inner event handler and the type of the actual event handler here. So the way we're going to resolve this is we're going to build a little wrapper function, and the wrapper function is going to perform the dynamic dispatch and attempt to go from the dynamic version of the event back to the original concrete typed version. So this is using downcasting, which is a feature that trait objects have in Rust. So we're going to do that now. So it's going to take an inner event, this function here, and actually we're going to want to move the function, and it's going to take the handler event as well, or rather it's going to take ownership of the handler. And we want to call this inner event, but the internal field, which is this box here, and now we're going to want to downcast it so in theory this downcast could fail here, and so I've got an unwrap, but in practice we already know that that it's not going to fail. The only reason it could fail is if two events decided to take the same name. So to handle that case, we're going to just do should we say incorrect. I'm just going to go for invalid event at the moment because it's quite a simple error message and we know what it means. I'll probably change it later. So there we go. Hopefully in compiling this, if I can move the window out of the way. Okay, now it almost likes us, so there's just one more thing we've got to do, and that is Okay, so downcast only works if the trait object implements the any trait. Now, any is kind of a special thing in Rust. It's usually an anti-pattern if you've seen it used. If you're seeing someone using any a lot in code, run like the wind, because it probably means they're using it in the wrong way. But in this case, we are using it in the correct way, because we actually do need dynamic dispatch. So we're going to require that event implements any, and in theory this should work, and it doesn't. Okay, I might need to switch this to any here. Right, yeah, so that seems to work, and now we've got another error. So we're going to sort that now. So the error is that this function here may not live long enough to sit within the bus. So it may not be able to store the event handler for long enough. So there is an option that allows us to add a static lifetime, which means this function is allowed to hang around until the end of time of it, effectively, or until the program ends. That would work, but it means that this type isn't quite as useful as it could be, and there are scenarios in which it wouldn't work, because sometimes you don't want a static here. So what we're going to do is we're going to make the entire bus type generic over a lifetime. And in most uses, this lifetime is probably just going to be static. But in cases where it's not, we can still use the type. So just adding the lifetime parameter. Okay. I think that should work. Oh, and another error. Okay. Oh, yeah. I missed the obvious thing, which is to handle this sum pattern. Okay, unused variable. That's fine. We've decided we're not going to implement this yet anyway. Cannot borrow as mutable. Okay, so what we need to do here is we just need to make this handler mutable, because we're going to be calling it here. Okay, and the compiler likes us, thank goodness, because this is quite a bizarre thing to be doing in Rust. And I'm very glad that worked, because it would be rather embarrassing if I spent the rest of the live stream getting confused. So now we're going to actually dispatch an event. So this is the interesting part. So what we're going to do is use something fairly similar to what we've done before here. So we're going to look up the event interned name in the listener map. So let me just check the docs just to make sure I'm doing the right thing. There's no such thing as a programmer that doesn't look at documentation. Okay, yeah. So we can just take this here. Oh, we're going to want to get mut actually. And then we're going to want to pass the event to every one of the listeners. So get mut is going to return an option, and that's fine because we might not have any listeners at all, in which case we just want to not do anything. So what we're going to do is we're going to only do something if there was at least one listener there. And the way we'll do that is like this. I should probably call this listeners, not listener. Okay. So for every listener in here, actually I'm just going to call this L's, it's shorter and it's already clear what it's doing. And I like short variable names. We're going to call the listener with the event, or rather the inner event in this case, as you can see, because that's the type signature. So first we're going to create an inner event. So we're just going to box our event here. So we're just going to turn this boxed event into a dynamic any box. And we're going to do L and then call it with inner event. Now that's a bit of a weird syntax, but it's needed because, or is it needed? No, it's not actually needed. So there we go. Okay. Let's see if the compiler gods like us this time. Oh, so we've got an error here, and the problem is that we're trying to pass this event to every single one of the listeners, and there might be multiple listeners, which means that we need to pass an event for each one, and this is going to mean that we need to duplicate this event. So there's a trait for this in Rust called clone. And what we're just going to do is we're just going to require that every dispatched event also takes or also implements clone. And oh, I've done something stupid. Yeah, so I'm just going to move this down here. No, and another thing we've done wrong. Rust can be very loving in a sort of a hard love way. It will scream at you until you get things right. And the compiler gods are happy now, so all good. So now we can actually test it. So let's try to run our test. So what we're going to do is I'm just going to add this no capture parameter, and this. So usually when you read a test, when you print things in a test, it won't display them on the screen on the terminal, and so we're going to add no capture, which means that it doesn't try to capture any output that the tests do, and this is quite useful because of course it tells us if the test is working. Okay, so we've got an error here because there's something in here. Add listener. Okay, so what we're going to need to do is just to move this here. Okay, one more thing. Yeah, so foo is not clone, which is exactly the constraint that we added here on the dispatch method. So what we're going to just do is going to just derive clone for foo. And here we go. We have received a foo, which is very good news. It means that this works. And it's really quite simple. You can see that just over 50 lines, I mean only 50 lines if you don't even count the imports. We've implemented a multi-threaded event dispatcher. It should be really quite fast. There are a few things we can do to make it even faster, like we can change the hashing algorithm that DashMap uses, but I think it's already using quite a fast one. So in theory, this should be extremely quick. What I'm going to do is, I think it might be worth writing a benchmark actually. So let me just, where can I go to find a good benchmark to test things with? always forget the benchmark syntax. So, right. So let's create a benches directory, and we're just going to call this one basic for now because I use that name a lot for just bog standard test-like things. So actually, I'm not going to remove that file. We're going to place the benchmark in here just because it's a bit easier. I'll probably move this out later. Excuse me. So Rust includes a built-in benchmarking system, and you can actually replace it out with better versions later if you want to, but the default one is pretty good. It's not perfect, but it does the job in a lot of cases. So what we're going to do is we're going to first create a bus. So this function gets called repeatedly during the process of benchmarking, and then it will calculate an average time to execute. So we're going to add a listener first of all. So we're going to do that like I'm just reading some documentation. I think I've got something. Okay, right, yeah. So what we're going to also import is this black box function, and this black box function basically it inhibits optimization. So in some cases, if we're trying to benchmark something, we might find that the compiler actually removes the code we're trying to benchmark because it's a bit too smart, and so this will basically just prevent that. So what we're going to do is we're going to start off with a counter, let's say. I. And we're going to do is that a good way of doing things? Maybe, maybe not. Okay, so actually I'm not going to have a counter at all. I've rethought that. I'm just going to add a listener. They're going to take the event, and it's just going to be a foo in this case, a bit like, well, it's just going to be this foo up here. And we're going to throw it into the black box, and so that we know it's definitely being created and it's being threaded all the way through to the listener. So now we're going to dispatch a load of foos. And now we're just going like that to see how long it takes. So hopefully I've not done anything wrong, although I probably have. It's very rare that you compile things without errors on the first go with Rust. Does anyone have any questions while we're waiting for this? Yeah, so this is a bit of a wild thing to fit into an hour-long live stream, especially if you're not really familiar with Rust. And even then, it's using a lot of black magic that is not very common to Rust code. Rust tends to sit extremely well in the static dispatch world, and we're throwing a load of dynamic dispatch at it. Oh dear, it seems my Discord has crashed without me noticing. Thank you, Discord, for doing that.
But the
There we
stream
go.
works.
You back, Joe?
Yeah.
All right.
You're back.
Okay.
How long have
perfect.
you been out? I didn't realise that it had crashed.
Yeah, you kicked out of the discussion for some reason.
Yeah, I think my Discord crashed.
Yeah. All right. Welcome back.
Right.
Yeah.
So, hopefully that's finished compiling now. And no, it has not. Why is it unresolved? Oh, wait. Okay, expected. Oh. Okay. Now we can hopefully benchmark it. Okay, so you can see it takes 31 nanoseconds to dispatch an event and have it be received by a listener. That's pretty darn fast. I'm just going to look it up in case I get it wrong. How many nanoseconds in a second? Because it's been some time since I studied physics. So
That 10 minus now 9?
yeah.
9?
So that means we can execute 1 billion of these in 30 seconds.
But can you make it faster?
Hmm?
Can you make it faster?
Probably somehow, but for a thing that's using thread local stuff, which is not free actually, thread local is fast, but it's not that fast. And I think in general, this method could be made a little bit faster with some magic. I'll have to think about how I do that. But yeah, for something that's doing dynamic dispatch and is allocating, although actually it's not allocating in this case, because foo is a zero size type, and so box isn't going to allocate any memory to it, which means that this code is entirely allocation free, apart from the allocation required to create a hash map, of course, and also the function here. Although actually that might also be allocation free because the function isn't stealing any of its environment. So yeah, this is basically allocation free and extremely fast. And of course it's not really an accurate test of how this might perform in the real world. In the real world, you're going to have a lot of different types of events, and you're going to have events with payloads that are quite heavy duty to move around and things like that. But in general, it's pretty quick. And this test is mostly measuring the overhead of everything else that's not a real world scenario. So what we're doing here is we're just measuring the overhead of boxing things and doing dynamic dispatch and so on. So yeah, it's kind of a credit to how fast Rust. In fact, actually, yeah, of course, Cargo Bench compiles with optimizations enabled, doesn't it? So there's one more thing that Alex, no, not Alex, I think it was Sam suggested to me yesterday, and that was instead of cloning the event, you can put the event inside an arc and do that instead. And that's very true, and that may avoid allocations in some case. So I'm going to do that now. Instead of a box, we're going to change it to an arc. I'm just going to import arc first. An arc is an atomic. Sorry, it's an atomic reference counted cell. Basically, it's like a box. It's basically a dynamically allocated region of memory that you can throw a thing into and then pass out handles to it to lots of other bits of code atomically. So it's all thread safe. So I think Arc supports trait objects. I'm pretty sure it does. So we can get rid of this clone, and we can get rid of the clone requirement because we're now using an arc. However, the one downside is that instead of taking the E directly, it's going to need to take a reference to E, because the arc is immutable, and so we can't take the E out of it because it may be used by other threads. So it should just be a case of doing this. Oh dear, it looks like Arc doesn't. Yeah, it looks like Arc doesn't support downcasting. What we might have to do then, it's a bit ugly. I'm sure I can improve this later. Yeah, that should work. Is to box the event inside the arc. I'm being silly. Okay, well, we have less red now. That's good. Okay, yep. So as expected, it's just expecting a reference to foo instead now, because we've made it only accept references. Okay, does not accept. 2. So we can clone this because arcs are virtually free to clone. It's just an atomic implement. It's just an atomic incrementation operation to clone an arc. Okay, so this might be an interesting one. I think I need to use downcast ref. Yes, actually I can use downcast ref, and this might let me get rid of the box as well. Okay, that works. So now I'm going to do is I'm going to get rid of the extra box because we shouldn't need that. There we go. That's nice. It works. That's nice to see. So now we've implemented Sam's proposal, which is to use an arc for passing around events instead. So yeah, this is a fairly powerful system, and if we take a look back at the original problem, which was how can a third party implement a new event? Well, it's quite easy. They just define a new type and they implement event for it. And then you can just throw those events into the event bus and they will work with B. So that makes things extremely easy. Are there any questions? I think we've pretty much come to the end. Are there any questions?
I do have a question.
Yeah.
Why is it slower than earlier?
That'll probably be the arc increment, or I don't know actually. There's probably some sort of clever trick the compiler could do in one specific case that it's no longer able to do, or something like that. It's hard to tell because we don't know the internals of all of these different types here.
Cool.
But hopefully this kind of overhead should basically vanish into nothing when it gets to a real world usage. The advantage, of course, here is that it's got slower because cloning an arc is a bit more expensive. But,
sure.
but on the plus side, if we had loads and loads of dispatchers, it would be faster. So if we had, say, 100 listeners or something, and they were all trying to listen in on the same event, then using an arc would be much faster than this.
So we are not requiring the events to be clonable now at all?
No, we're not. The events don't need to be cloned. They just need to implement this trait. And because this method has got a default implementation, literally all you need to do is this, and you can throw your event around.
Yeah, that's nice.
Sorry.
That's nice because just before the live, I tried something, and I was blocked at some point because I wanted to create an event when we receive a new transaction, but the transaction type is not clonable. Is not copyable, not clonable, and it shouldn't be.
Yeah.
So I would have been blocked.
Yeah. I mean, the only disadvantage here is that instead of getting the original event out the end, you only get a reference to the event. But that's not so bad. If you really want the data inside it, you can just clone the data from inside it. Or if foo already implements clone, then you can quite easily clone foo if you so wish. And it works fine. So you can clone it at the receiver side. What you could also do in practice is, because a lot of B is asynchronous, you might want to have a listener that throws the event into an MPSC, a channel, a multi-threaded channel, and then you can send the event to other threads or whatever, or other tasks. So yeah, in general, it should be a pretty portable piece of code, and it doesn't really depend on anything else apart from obviously all of the dependencies we've got.
Oh, awesome.
Right, are there any more questions in the chat? Nothing. Fair enough. Okay. Okay, so we'll presumably see you next week. I don't know who's doing it next week, but thanks for watching.
I think it would be me.
Right, okay. You'll see T-Bone next week then.
Yeah, thanks everyone for watching and see you next week.
Okay.
That's a really nice one.
Cheers all.
Bye.